Welcome back to the morning show. Time now for part 2 of our Wise Guy segment. Mr. Matt Selen, our physics professor from the U of I, joined us. Continue our discussion about lucky numbers and randomness and how that equates to gas and explosions.
Yeah, so we'll get to the gas and explosions here. This time we'll watch the time. I'm sorry about that.
No
so
worries.
anyways,
No worries.
Where I was going with this whole coin flipping thing was that if you flip a coin 10 times,
right,
and you repeat that experiment over and over and over and over again, and you just look at how many times it comes up heads each time you do 10, then about 2/3 of the time you're going to get a number that's sort of between 3 and 7. Okay. Sort of, it's the uncertainty is pretty big. If you do the same thing, if you flip a coin, let's say 100 times, the average is going to be maybe 50 heads. But now it's going to be sort of 2/3 of the time it'll be between 40 and 50. If you flip a coin 1,000 times, then it'll be 500, as the average that you're going to get ahead. But now the uncertainty is between, let's say, 470 and 530. So while the uncertainty kind of gets bigger, the relative uncertainty, if you compare that 500 or the 30 uncertainty to the 1,000 you picked, that ratio is still a much smaller error. So if you, for example, flipped it 100,000 times, then the uncertainty in the answer you're going to get is only going to be 1%. So that's why you always want to, ask a large number of people when you're pulling. Okay, so now this has to do with gas, how you may be asking at this point, and explosions. And I'll tell you, the way that gas molecules move has to do with randomness, because it moves a little distance, it has a little collision, it moves in a different direction, it has a collision, moves in a different direction. You can kind of model this by flipping a coin. If you take a coin and you flip a head, if you take one step forward, if you flip a head, if you flip a tail, you take one step backward.
Oh, I see.
And suppose you did that 10 times.
Just be all about the room.
Then on average, you're not going to go anywhere, but the uncertainty in where you are, if you flip it 10 times, is going to be a couple of steps in each direction.
I see.
Okay? If you flip it 100 times, then it's about 10 steps. If you flip it 10,000 times, it's going to be maybe 100 steps or something like that. Okay? So what happens is that if you want the average distance you've sort of moved from where you began, if you want that number to double, you have to repeat the experiment 4 times as many times.
Okay.
So it goes like this. Okay. So that means that if you put two gases together, then they mix by this sort of random process. And it turns out that, and we talked about this last time I was here, the same reason you smell flowers on the other side of the room is because the little things have to bounce around, and it takes them a long time to get there. Okay. So now, what this has to do with gases and explosions, we're getting there now, okay, is this following, that if you have a little balloon that's full of, let's say, hydrogen gas, and if I want to light this on fire, it's going to explode. Okay, and I'll do that in a second. The way that something explodes, the way something burns, in the case of hydrogen and everything else, is it has to mix with oxygen, and then the hydrogen combines with oxygen, and you get the flash and the bang. Okay, now if right now the hydrogen is all inside the balloon, the oxygen is all outside the balloon. So the way that this has to burn is that the oxygen that's outside, once the balloon bursts, it has to kind of diffuse in and mix with the hydrogen, which takes time. So what you're going to hear when we do this is that the explosion is very different when you have just hydrogen in here and the oxygen has to mix in, because it takes a while, than if you already have the oxygen mixed in, because it's going to go really quickly. Okay, so
1 minute to go here.
That's good. So we're going to start with the hydrogen balloon, and we're going to hope this isn't going to be too big a bang.
All right, stand by.
Camera on there. Okay. Okay. So that wasn't so bad, but you saw that you got a nice yellow flame and it went pop. This balloon has the oxygen mixed in it already.
So this one should be.
This should be different. You can tell me how it's different.
All right. A little deeper.
Right, and if you actually look at it, I'll do it again here, real quick, because it's fun, and you can do it this time. Okay.
Yes.
We'll just do it with the one that's already mixed. Okay, because it's fantastically good. Okay, now I'm going to hold my ears.
You ready?
Yeah. Okay. All right. So I'm going to leave you guys with these. So the point, by the way.
Wait, you're leaving the torch?
No, I'm going to leave this. Okay, Robert, you want to do this?
Come on in here, Reese.
Okay. See which one you like the best. Now do the other one.
That was a good one. That was a better one.
That was a better one. Okay. So what we learned here is that when the oxygen has to diffuse, has to do this random little jiggling around to mix together as it's burning, then it just takes longer, and you get sort of a lower thunk because it takes longer, and you get it happens slower. If you want a fantastic explosion, you want to have the oxygen in there already.
Okay.
That's what we learned.
Good advice.
Okay.
Thank you, sir.
And it's
Dunkitude. All right, if you want to see a replay of this, it's on our website. We'll be right back.